is Carlos Meza. I'm from the University of Applied Sciences of Anhalt. And actually this work, I should say, has been done by Mario Araya, who was part of his master thesis. He couldn't come here. And from the Costa Rica Institute of Technology. And we also did this from some colleagues from the microelectronic engineering department, Carlos Salazar and Alfonso Chacón, also from the Costa Rica Institute of Technology. What we wanted to do is we wanted to analyze bus-based microgrid systems. So a bus-based microgrid system is a system in which you connect the different elements. It could be generation elements, storage elements, or even loads through buses. Right? So you may have one bus, as you see here. It's one bus, or different storages, or multi-bus systems. And basically, the motivation was that we wanted to study. So what we were doing was we wanted to study the power electronics that are involved in these microgrids. We want to study two parts: the transient behavior of these power converters, and also the ripple. And to do this, you may do two things. So basically, you may construct a microgrid system, or you may work on simulations. And then sometimes, if you do it, you build your microgrid system. You may then will be spending some time, then building some money that maybe not be the microgrid that you were looking for. I should say that for the ripple, we wanted to continue this work we did with Professor Ortega from Supélec, France, in which we get very interesting results in which just by looking at the ripple of power converters, we were able to estimate different parameters of the input or the output of the power converter. And with that, we wanted to say, okay, there was with one element, we say, what happens if we start to analyze the different ripples in a microgrid setting? And so then the idea was, let's study this and let's try to work on simulations. And in order to get all these aspects of simulation, of modeling in a microgrid system for power converters, you require basically algebraic and differential equations. So for the algebraic equations, it's quite simple, as you can see here. Just basically basic circuit equations in which you have the voltages should be the same in each bus, and then the currents will be the sum of currents in the bus should be 0. And then you will do that for all the different buses, right? And for the dynamic equation, what you need to do is just take all the elements that contribute to the dynamic behavior of the system. Basically, that's the inductors and the capacitors that you have in your power converters. And with that, you have a set of differential equations, as you can see here. So these differential equations, you will have n plus m differential equations, in which n is the number of capacitors, m is the number of inductors. With that, you will have a very good idea of what is modeling of what is happening in your microgrid. And then we are only missing the control signal that will be affecting these different converters. The control signal is basically another differential equation. It could be a first order differential equation, we have FPGA, or a second order differential equations. So by the end, if you really want to get all the dynamic behavior of a microgrid system, you need to consider n number of capacitors plus m plus nu, the number of different control elements, first order differential equation of, if you want, n plus m plus nu order differential equation. And that even for a small system would be quite high order system. And on top of that, what we wanted to do is also to analyze the ripple. So the integration step that you need to use to get the ripple effects should be at least 10 times smaller than the switching frequency that you have. So that we're talking about microseconds, even nanoseconds if you have hundreds of kilohertz switching time. That is, so we wanted to have this, we wanted to simulate this, and if we are able to get this, we will have a very good dynamic behavior of a microgrid system. We wanted to start with a specific example, so we used this one, proposed by Maduri and George Verghese from MIT. They actually have a multi-bus DC system. So you have here a high voltage, which is 400 volts. Okay. 400 volts in here, you have 50 volts, and then you have a smaller voltage here of 24 volts. This is usually done for villages. Very quite interesting structure. And then what we did is, okay, we took this, applied our modeling, so just program different differential equations, and tried in 3 different systems. One was the sim, power sim, which is kind of the, I would say, what most people are using when you analyze power converters. So it's a commercial-based PSpice simulator. We programmed that on Python. That is quite interesting by itself, because what we did is every differential equation was an object that we were able to program. So it was object-oriented programming. And then also we implement this in hardware. And the idea was, first of all, how they compare to each other, to validate them among each other, and then to see how long they last. And we did that, and then we compared that with the theoretical response. So this is the steady state value that we get from the differential equations. And then from the results that we have from PC, Python, and then with hardware. And we were able to see that the difference was greater than 2% for the case of the current. But still they were quite well among each other. And the most important part for us is not only the steady state value, but it's also the shape of the dynamic behavior. This is what we wanted to analyze. But the most interesting results are these ones shown here. I think the resolution is not very nice, but then, so what we have here is the time in the y-axis here, and then here is the, so this is the simulation time, and here what we have is the number of systems that you have, right? So what we did is we tried different sizes of microgrids, right? So with one demand control load up to 10 demand control load, and what we see is how much it takes to do the simulation. And what you can see is that with Python, you will have a quite steep slope in here, and that would be this one here. That would be the simulation with the hardwired system, right? Which actually you cannot see the difference. Here you have all the different cases. Here you have it one on top of the other. Actually, you will have to zoom this in order to see the difference. So then the hardware base, that is as expected, allow us to get more complex microgrid system without affecting the simulation time of our microgrid. Of course, there are some issues that I won't get into detail because of time, but you need to do the programming in hardware very carefully, because you may get some strange behaviors like this. This is due mainly because of the integration time, but you will also have some effects about the numerical representation that you use. And what we have seen here is, of course, if you have a long integration time for your simulation, you will have these dynamic behaviors that do not correspond to the behavior of the microgrid system. However, then we were able to derive a constraint which is about 25 to 50 times smaller the integration frequency than the integration period than the switching period, in which we're able to get very good results to compare to the theoretical values. Yeah, so as conclusion, I would say that then we were able to have a quite interesting simulation program implemented in hardware that allow us to simulate complex microgrid, which in a very short time. And as future work, what we want to do this is not only to use it as a way of simulating different scenarios in a very short time, but also use it as a way of a digital twin, something that can be running with a real microgrid in parallel, and then be able to detect these different faults or situations in parallel. And with that, then I would like to thank you for your attention. I think I also stick with the time.
Thank you, Carlos. That's great. Can you just ask a question? You talked about the accuracy of your simulation. Why it's important? Why the 2% or is accuracy important? I'm just trying to make sense in real life.
Right.
You know?
Yeah, so the steady state values are, well, what we need to understand is that for us, the most important part was the dynamic behavior that you have within the different units, because that might lead to some stability when you have all the different elements connected with each other. So that the steady state behavior was not such important for us, but just to validate our proposal with the other ones.
Okay, that's great, thanks. And invite you for another question, please.
Can you give an idea of how big your microgrids can get on your FPGA?
Yeah, so then it can be up to 10. All depends on the size of the FPGA. So we were using, I would say, a low size FPGA. It was not one of the biggest. It was 300 euros more or less. That allows us to get 3 different PV arrays. So that if you get to this part here, so that would be 3 different sources with 10 different loads. With so that would be around 20th order differential equation. And then you can have many options. One is have a bigger FPGA or have a cluster of FPGAs. So you can stack them with each other and then have some more computer. And then you can then duplicate the number of microgrids that you want. Again, that will be for a small system, of course. Then that will be, if you want to scale it to a big city, that will not be. But then you will want dribble in a system, right?
Yes. Thank you very much, Carlos. Thanks.